All right, it's me again with Learning Target 14, orders of reactions. What do they mean? So we can break this learning target into two pieces. One, we can learn how to correlate concentration versus time data to the order of reaction. And two, we're going to identify functions that linearize rate equations in order to find the rate constant, or K. Now, if you are in calculus, this is also known as finding the integral. So if you find an easier, faster, more efficient way of doing this calculus, besides what I'm going to teach you just manually with a graph, go for it, do it. Remember, IB Chem assumes that you haven't had calculus yet. So let's look at a review here. Learning Target 13, we learned how to derive a rate law, and we found the rate law to be this, where rate is going to be a constant, and this rate constant will have a variety of different units based upon what order of reaction you have. You have concentration of a reactant to the X power, concentration of a reactant to the Y power, and this could go on and on and on depending on how many reactants I have. We're just going to deal with two here. And X and Y are orders of the reactants that we calculated experimentally, but we can also get those by looking at a graph, which you will see in the next few slides. The simplest form is the zero order reaction. Zero order reactions with respective to one of the reactants or products, we're just going to use reactants here, take on this form, where R is going to be your rate constant, concentration of some reactant to the zero power. And it's really sweet because that just means that the rate is equal to the rate constant. When I graph concentration versus time, which you will notice time is not present in this equation, you will get a linear equation. And the nice thing here is, since it's already linear, the rate constant is going to be the slope, negative because the amount of reactant is decreasing over time. So the function for this graph here is going to be almost the exact same thing as the rate equation, because the amount of reactant that is changing over time will not change, the rate does not change. Let's look at some example data. I'll say that again, as concentration changes, the rate of reaction does not. So here is some data of a zero order reaction. And I will show you a little bit later how I know it's zero order. And we're going to decompose here some N2O5. It's going to decompose into stuff. And there's so many different options. I don't care what stuff I'm making. I'm just caring the rate that the N2O5 is breaking apart. If I was to do a concentration versus time graph with this, I would have concentration on my y-axis, time on my x-axis, and I do a linear regression, and I did this one myself on Google Sheets. And when I did this linear regression on Google Sheets, I get a linear equation where the rate constant is my slope. And I know it's zero order because once I plotted this data, did my correlation value, my R squared, and it's incredibly close to 1. So I know immediately that it's zero order and can read right off the graph what the slope is, and that's going to be my rate equation, or excuse me, my rate constant. So if I was to graph my original rate law, we can now see, because the rate is equal to the rate constant, I will get this graph here, where the slope of the line, which was the negative 0.196, is graphed here like this, and it doesn't change. Oops. You'll know this from calculus as being the derivative of this graph. The derivative of a straight line or a linear graph is just going to be linear but with no slope. So there's a couple different ways we can look at this data here and notice that it's a zero order equation. You might not even have to graph by analyzing this data. This is just one strategy to figure out if it's zero order. If you need a review on how to graph using Google Sheets or a graphing calculator, or you need some tips on how to get started with graphing, please let me know. So unfortunately, that's the easiest scenario when we've got a zero order rate law. But if we have a first order, second order, or other order rate law, we have to perform this procedure where we are linearizing a graph of time versus concentration data. Now, again, there could be another way of doing this that you learned in calculus, or another intuitive way where you can just look at the data to do this. If you want to use that method to figure out the order of the reaction, be my guest. This is the way that IB recommends for students who are not in calculus. So instead of calling it finding the integral, we're going to call it linearizing a graph. And there's two things to know about why we linearize rate laws. One, when we find a function that creates the straight line from the data, the rate constant is the slope. So if I can make my linear function, I can look at that function, read the slope, I got my rate constant. And that'll allow me to put it into the rate law. And two, the function that linearizes the data allows us to find concentration versus time. Our rate law does not allow us to do that. And if I was to do a concentration versus time graph for a first order, second order, and so on and so forth, I wouldn't be able to get that as well. So what I can do is find a function that allows me to find a concentration at any moment in time. So let's look at first order. So first order reaction takes on the following form, as you predicted. So we got the rate equals rate constant times concentration to the first power. Or if I double that concentration, it's going to also double the rate. Doubling the concentration will double the rate. If I was to graph concentration versus time, which is not this equation here, but another set of data where I will try to come up with this equation, it looks like exponential decay, because every time I halve the concentration, I will half the rate. So first order reactions are exponential decay. You could get into this talking about half-life and so on and so forth. We are going to skip that in the distance learning model. As concentration is half, so is the rate of reaction. And that is one of the indicators that you've got exponential decay. So here's some example data. I like decomposition reactions for these examples because there's only one reactant. Here's some that I just picked up off of a worksheet. Here is the graph of concentration versus time. You'll notice that it's exponential decay because there is my function that I fitted to the graph. And I didn't put the r-squared value, but it's in the 0.9-ish or above, I promise you. And if I look at this graph here, I can't really figure out what k is. I can't find my rate constant because it does not have this in terms of a function that allows me to find a straight line. So what I'm going to do is I'm going to now graph my rate of decomposition over time, which allows me to do this by finding the natural log of the concentration of my reactant, C4H6. If I find the natural log of a first order reaction, all of a sudden I get a straight line. And now that I've got a straight line, I can say the natural log of the concentration of C4H6 is going to give me my rate constant. I can find that here by doing my linear regression. I did put my r-squared value, that it's about 0.98, and that means that that slope is going to be my k value. That slope is going to give me my rate constant. So that is the beauty of linearizing graphs. I will then be able to figure out what my rate constant is. Second order reactions. So second order reactions take on this form. Not surprising, but this means that as the concentration doubles, the rate of decay is going to quadruple, or else known as quadratic. So if I do a concentration versus time graph, it's going to take that quadratic form. As concentration changes, ignore that little blip in the previous. We left off with figuring out concentration versus time is going to take on a quadratic form in the rate law. Here's some example second order data. I couldn't find data to have a specific reaction, so I just kind of made some up. And let's pretend we have the decomposition of something. We're decomposing something that's second order. The rate data that I came up with looks like this. A concentration versus time graph is going to look like this. And you will notice here that when I did my quadratic fit in Google Sheets, that I'm going to get a nice quadratic equation here, just like that. By the way, this little symbol here, little m over by the m, is millimolar. So that means a millionth of a mole, just to let you know. Now, if I was to, and I'm just telling you that some calculus is involved here, if I was to take these reactants and find the inverse, I can graph the integrated rate of decomposition versus time. And lo and behold, it turns linear. And I'm going to have here a beautiful linear equation. And when I've got that linear equation, lo and behold, I've got my slope. And my slope is going to give me my rate constant, which I can fill into an experimental rate law. So notice here the difference between zero order and first order for a reactant is because I'm finding the inverse, my K value is now positive and not negative. So that's the only difference here for second order data. The K value is positive. So this is a lot of information, a lot of graphing, and I didn't hand graph these myself to show you what I did. So and before I get to that, let's look at third, fourth, fifth, and sixth order data. So third, fourth, fifth, sixth order equations, so on and so forth. Just kidding, they exist, but IB doesn't care. We're not going to get into those. So I put that in there to scare you if it worked or not. But here's the big summary chart for you to take a look at. So again, we're not getting deep into the calculus with these things. What we're looking for is the differentiated or the rate law that we calculated before. Figure out how to linearize the graph. What are we going to graph to give us a linear function? And then what integrated rate law gets paired with the original rate law, experimental rate law, or differentiated rate law. All three mean the same thing. So zero order, once again, I don't have to do anything to it because both the differentiated rate law and the integrated rate law are linear. First order rate law, if I graph the natural log of the concentration of the reactant versus time, I'll get a straight line that has this form. Second order looks like this. If I graph the inverse of the concentration versus time, I will get this function here, and the K, again, is going to be positive for my rate constant. This is the big takeaway from Learning Target 14. This is the big piece right here. I would pause the video at this point, make this beautiful graph or table, because this is what you're going to use in the next piece. All right, last bit, problem-solving tips. When I give you questions that go along with Learning Target 14, I'm going to give you data tables. Data tables that are going to be time and concentration. So you will encounter those concentration versus time data tables, and you're going to be tasked to decide the order of reaction. Again, you can do this using your fancy calculus if you're the calculus master, or you know how to do this by finding differences in the y values on your table. That's another way you could do this. Or here's the graphing method that IB likes. Not better, just what they suggest. First thing everybody does is create a graph of the concentration of A versus time. So if I graph using Google Sheets or I use your graphing calculator and I find that that graph is linear, it's zero order, the slope is your rate constant, and boom, you're done. If not, the next step that you do, you make a graph that graphs the natural log of the concentration of your reactant versus time. If you graph the concentration of your reactant versus time, natural log that, and that graph is going to be linear. It's first order, and the slope is k, a negative value, and you're done. If not, you're going to create a graph where on the y-axis you'll have 1 over the concentration of your reactant versus time. If the inverse of the concentration versus time graph is linear, boom, it's second order. The slope is going to be positive k, and then you're done. And if it's none of that stuff, the problem I gave you is beyond the scope of IB chemistry, and you can complain to me about that, because I think I only put into your worksheet first, second, and zero order reactions. So there's a lot there. A lot I feel like I skipped. I'm going to attach the video for how to graph on Google Sheets to help you with this particular learning target. If they have asked you to graph at any point in time with a graphing calculator in any of your math classes, I highly suggest that as well. And if you need any assistance with that, please let me know. All right, thank you for making it to the end. The worksheet's attached. Have a lovely afternoon.